Hi, everyone. Um, all right, so this is going to be a very speedy lecture, so keep your heads up and listen closely. So good morning, my name is Amit Mandelbaum. I'm the co-founder and CTO of Everminds. And today I have the privilege to talk to you about what I think is one of the most fascinating areas in LLMs, and which was actually mentioned 2 times today already. It's the AI agents. I think it's still a pretty, I think most of you probably heard about like AutoGPT or Baby AGI by this point. I think most of you probably didn't try it. And even if you did, you thought that it's not really working. But I still think that this is one of the most interesting areas today. And I saw like amazing demos of agents. So in this like pretty short lecture, I will try to delve into the foundational papers and concept in this area. I will also show a hands-on demo of a code that I wrote from scratch, no LangChain involved, of using agents that can search Google and code Python and execute the code and then combine the two. And finally, I will also discuss how we at Everminds are using LLM agents in order to change the way people work together. So let's get into it. So agents in general in artificial intelligence is definitely not a novel concept. The basic artificial intelligence research started in the 60s and 70s was talking mainly about agents. In the concept of machine learning or deep learning, deep reinforcement learning or reinforcement learning is a concept where we have an agent. An agent is some sort of a model. It doesn't matter if it's like based on machine learning or deep learning. This agent has a goal, and it has some sort of policy, which is a way to achieve this goal. The agent can do an action on an external environment, gets back a feedback, and then compare the observation with the reward and the policy to perform the next action, and then it continues to do so until it reaches its goal. And this is how the basic notion of agents. If we move this concept to LLMs, the agent now is a GPT advanced model. Doesn't have to be GPT, but works well with it. With special prompting, like the ones we already saw, like chain of thoughts prompting, and we'll see much more of this in this lecture. The agent can also have an external memory. It can also have other agents, which we'll see later for utility tasks like memory management and task management. It has a reward function, and the reward function can be dictated by a human in the loop or by the agent itself, which is a very interesting idea. And it performs action on an environment which have external tools like coding, browsing, and search. And it can also talk to other LLM agents, like in a multi-agent system like we know. And it gets back an observation in the same way. And in this short time, I plan to delve into each of the components of the system and show you what I think are the foundational papers for creating this kind of environment and in this kind of concept. I would say this list of papers is by no means exhaustive. You have new interesting papers coming basically on a daily basis, but you can start with it and take it into further reading. So the first, and I think one of the most famous papers in this area is the React paper. This was written in a collaboration between Princeton University and Google Brain. And in this paper, the authors examined 3 distinct types of prompting techniques. First one, which was already mentioned here a couple of times, is the chain of thought prompting, which is basically a very fancy name for think it step by step. There are some variations of it, but basically this is it. And in specific papers, they use it in the few shot setup, where they give few examples for the prompt and the answer. The second one is the act prompting. The act prompting, which only works like once, it's not a loop yet, is do an action, get an observation back from like the action that you did. If you did an action with like you search, then you get back the search result. and then give the final answer. So if someone tells me to search something in Wikipedia, it uses the Wikipedia search, gets back the answer, and gives the answer back to the user. And finally, and the most important one, is the React prompting, which was actually the first one to really create a sort of a loop which resembles the concept of agent. In this prompting, the agent have a thought, which is a sort of a planning or reflection of what I need to do. It performs an action based on this thought. It gets an observation, and then it continues this kind of loop until it reaches resolution, which would be basically answering what the user asked him. And this, in this sense, this is the first one that really shows how smart prompting can actually create this sort of a loop of an agent performing an action on an environment, getting back an observation, and doing it in a loop until resolution. And in this paper, the authors demonstrate that applying this kind of React prompting is very, very good and gives significant improvement on tasks that require multi-step actions. Like, for example, if I have a question which requires multi-step operations, or if I have some decision-making game that I need to take multiple steps, then the React prompting works much better than other ones. But more importantly, the true value of the React prompting lies in that it became the foundational way of having LLMs use external tools, in the sense that you can get any tool, you can get a task, you can get a list of tools with their natural language description and their API. The agent then thinks how to use this kind of tools, act with this kind of tools, observe the results, and then repeats this loop until completion. And now we'll do a short break from the lecture and actually show you how this actually works. Okay. All right. So as I said, I wrote this code like from scratch. I didn't really code it. There is a really good tutorial online, which is partially based on a source code of LangChain. So first of all, we install OpenAI. This one is pretty self-understood. And then we create our first tool, which is a basic Google search tool. And we need to remember that for any tool that we create for the agent, the most important thing is the API through for the agent, the LLM agent, and a natural language description. And I think for me, basically this concept, it's really amazing that we give a natural language description to the model and then it knows how to use it. So this is what we do here. You can ignore most of the code, some configurations, but eventually this is the definition of the tool. We give it a headline, tool for Google search result. It is named Google search, and then we give it some sort of description. This is what we give in the prompt to the model. It doesn't see anything else. Get specific information from search tray, input should be question like whatever, and the result will be the answer to the question, and then you see, it just do a very simple, the input text is coming from the prompt, and it does this kind of search on Google. And we can see an example for the tool usage. So I asked him who is Amit Mandelbaum, and I actually gave me a pretty good idea, deep learning researcher, senior data scientist, etc. So this is working. This is pretty nice. The next step is we need to define the language model itself. So yeah, don't copy my API key. We use GPT-4. I have access to GPT-4, but it does work to some extent with GPT 3.5 as well. And basically, a very simple generation. Yeah, you probably know this. We have a response, we have a prompt, and that's it. And then let's test the model. So we define the model, the chat LLM, and then we said who is president of the USA. And as you know, he's not updated until today, but it says, as far as my knowledge go, the president is Joe Biden, which is still correct. Okay, so this is just the basic definitions. The next step is to define the React prompt, which is the most like where the magic lies. So you can see the prompt here, and there is two important components. First one is the special tokens that we use. Whenever we want to use agents, we need to have a sort of special tokens which define the system, a sort of like a coding language, but in natural language. So we have the final answer token, which is used for us to understand that the model has finished what it needs to do. We have the observation tokens, which help us see, we'll see in a minute, that it doesn't go into a sort of an infinite loop. And we have the thought token, which means that after that, we'll have a sort of an action that we need to perform on the external tool. And this is basically the React prompt in a nutshell. So usually we say today is, we give it the date because we want it to be able to have some knowledge that is relevant to the current time, and then answer the question best as you can by using the following tools. Here we just give it a list of tools. This is basically only limited by the context window. So we are not really limited by the number of tools we can give him. Use the following format. Question is the question that the user asks. Thought is something that the model itself says. This is not something that we give the model. Action is the tool, the agent itself dictates the action. And then it dictates like what the exact input gets back an observation. And this is something we give back to the model. And then there is a thought. And if the thought is now I know the final answer, then it would usually just give the final answer. But most time, as we'll see, it goes at least several steps before completing the action. And okay, so this is the prompt. And here we basically define the agent. It's basically very generic code. We just define the tool description, the tool names, and then we do the running loop. So notice here several interesting things. First one is that we always feed, we do sort of a loop. So we always feed the prompt with the previous responders because we need to have some sort of a conversational environment. We also define the number of loops. We don't want to, I think some of you have used AutoGPT. One of its main problems that it's get into an infinite loop. So we want to be limiting the model to not go in infinite loop. Here, max loops is defined as 10. And as you can see, if it asks to use the tool final answer, then we know that it finished its work. We can also handle some errors if it tries to access some unknown tool. And we also try to, just a minute. Yeah, I skipped it. We also want it to not go in infinite loop. And usually this kind of agents, they go in infinite loop if they do an observation after observation and then again and again until they get stuck. So once we recognize that there is an observation after an observation, we stop the agent. And then we have this sort of decide of the next action, which is usually based on the observation. And then here we just do some sort of a passing of the action because eventually the agent is talking in a natural language. And I think one of the reasons this works much better with GPT-4 compared to GPT 3.5 is that GPT-4 is much, much better than giving output in an exact format, like JSON format or something that we can parse automatically. So this is what we do here. We use some sort of a regular expression. Of course, here we handle error as well. But basically, this is what we do here. We have a prompt, we have a sort of a loop, some special tokens to understand where is the final answer coming, and then we just use it. So I give it this sort of task. We have the agent, the React agent, and I ask him which movie, it was not even spelled correctly, but it understands me, which movie generated more money, Avengers 1 or Avengers 2. And this is the full prompt as you see it. Today is this day. We give it the Google search with its description. We give it the React prompt, and then we say begin. And then we give the user a question, which movie generated more money, Avengers 1 or 2? And this is really fascinating to see the thinking process of the agent. So it says, I need to find the box office earning for both Avengers 1 and 2. Action, Google search. This is the agent is writing. We are not writing any of this. And then the action input is Avengers 1 box office earnings. It gets it back, and then it says, GPT, I found the box office earnings, but I still need to find for Avengers 2, do the Google search again, gets it back, and then give me the final answer. Final answer is Avenger 1 generated more money, and then it explained why, which is exactly the correct answer, which is very, very impressive. So this entire thinking process was completely autonomous. I didn't try anything here. So this is a very nice example. So I say, okay, let's try to make things a bit harder. And now we want the agent to be also able to write Python code and execute it. So we build this sort of a Python execution code, which is based on Replit. You can ignore the code, it's not super interesting. But here again, we give a natural language description, a tool for running Python code in REPL. And then we say a Python shell, use this to execute Python commands, introduce a valid Python command. And if you want to see the output value, you should print it out with print. And this is basically like the essence of the tool. Everything else is not super important. And this is what's going to go inside the prompt. So we test it, and it works really well. And now we want to test the agent with Google search and Python together and see if it's actually able to work. So I give it some pretty complicated question. Find me the cost of fuel of flying between Tel Aviv to Houston in ILS. Use Python. So for this, it needs to gather many, many pieces of information, and let's see how this goes. So this is the full prompt. I gave him the two tools, like you can see, Google search. We have Google search, we have the Python REPL, and then we give him the prompt again, the React prompt, and then the question. So the first one, he thinks like all the pieces of data that he needs to get. So we need to find the distance between Tel Aviv and Houston, average fuel consumption by an airplane, cost of a jet fuel, and the conversion rate between USD and ILS, and just from a simple question, how it was able to understand so many details of the thing that you need to do, and then it started performing. So first it searched for the distance between Tel Aviv and Houston, then it do the average fuel consumption, and then the cost of jet fuel, and then the conversion rate, and it gets all this information pretty accurately, and then it does the code. And here we already see one of the problems with a language model, that sometimes they take your input pretty literally. And when I say use Python, it's write a Python code, but it also puts in the beginning of the Python code the word Python, which is a syntax error. But luckily for us, it's a very smart model. So it gets back this kind of error and knows I made a mistake by including Python in the action input. I will remove it and try again. And this is, by the way, something very interesting. GPT-4 gets this kind of observation, and I saw it several times, but it only fixes it after the second time it gets this error. So you see that he understands the error, but it makes the same error again. And then, again, I made a mistake again. Yes, it even said that I make a mistake again. And the action input, I will remove it again, and then it performs the code. Look how it combined all the search results into the code, did the correct calculation, and again gave me a result, which is, yes, a bit above 1,200 ILS. What's the problem here? That this is the cost per passenger, which is something that he ignored when he got back the search results. But for me, it's like mind-blowing. So many steps that he had to do. So agents in the flesh. All right, so we'll continue with the lecture. How much time do we got? Okay, we have some time. All right, so we talked about the React, and okay, so we saw that planning is a very foundational. Right. Okay, so as we saw, the React agent uses the thinking and planning to approach a given task, and in these two papers that they dive a bit more into the area of planning. So in the first paper published by researchers from China and Singapore, the authors show that using planning for even with a simple chain of thought prompting can improve results dramatically on arithmetic tasks, especially arithmetic tasks that have multi-step calculation, as they show here. And by the way, a very recent paper by OpenAI was published last week with, it was a bit more complicated, but had about the same idea. And the second one, which this is not an actual real paper, but I think it one, if we talk about agent, I think this is one of the most popular tools today. It's called Baby AGI. It was published by Nakajima, which I also really recommend following on Twitter. And in this work, Nakajima created an agent named Baby AGI. The agent is getting a primary goal from the user, can be a very broad and general goal, and then it uses other LLM agents to take this general goal, break it into many subtasks, and then start executing them. And also it uses external memory and other agents to reprioritize. So you get an observation like to one of the tests that you made, and maybe you get a completion of this task, and then you create maybe new tests, and then reprioritize the tests that you already have. So this is something that exemplifies very nicely the use of other LLM agents for utility tasks, like memory management, prioritizing tests, and creating tests. And also, this is the first step towards completely autonomous agent. And I think I saw this really cool website, which is called, I think, aiagents.ai, something like that, that is using Baby AGI. And they seem to have a real working product, which looks pretty nice. So you can check it out. Another important aspect is the reward, or in our context, self-reward mechanism of LLM agents. So in the first paper, researchers from Microsoft and Columbia University, they developed a reinforcement learning framework for agents that need to answer some question based on external knowledge. So what happens here is that the user asks some question, the agent is connected to a sort of external knowledge like Wikipedia or web search or something like this. And then there is this kind of utility function, which is checking the results of the model and then knows to correct the prompt if the result is not good enough. And what do you mean by not good enough? Maybe the answer to the question does not appear in the external knowledge. Maybe it has some sort of hallucinations. Or for example, if someone orders a place in a restaurant, it needs to have a more, I don't know, polite response. So the utility function, which is basically a reinforcement learning framework within this kind of AI agent system, is fixing the prompt of the agent until it reaches the optimal response. And then they show that in many, that it gets a pretty significant boost in performance on tasks that use this kind of framework of using external knowledge. Another interesting paper, which is also starting to become pretty famous, is the reflection with an X paper, an autonomous agent with dynamics memory and self-reflection. So what happens in this paper is that they take the React agent, and then over the React agent, they put another reinforcement learning framework, which basically does this. It observes the agent, it gets like a sort of a heuristic, a history of actions and observations that the first React agent did, and some reward function, which basically means, did the agent perform his task correctly by this point? And then here we have some sort of a learning algorithm that knows to reflect on this and change and fix the prompt of the first agent. So we have one LLM agent, which is fixing the prompt for the other LLM agent to actually help it perform its tasks better. And this works actually very well. It takes quite a lot of complex tasks that the React agent without any reflection is okay performing like 35% of the time, and actually in few tries boost its performance very, very significantly. So I think one of the most important aspects of this paper that it shows that the potential of LLM agent is far, far more broader than we might see in first glance, and using sophisticated techniques like reflection can really boost the performance and maybe perform things that we can't even do. There was another interesting paper that came out recently that they took a test that was thought to be completely impossible by GPT-4, and using this sort of reflection mechanism, they achieved something like 75% success, which was really mind-blowing. A very recent paper, which was published around 2 weeks ago by NVIDIA and several universities, takes all this component together and builds an agent that is able to play Minecraft. And you may be saying, okay, well, Minecraft is not that of an interesting game, but it is, because the things that we learn from here are very important for basically every sort of application that we want to do with agents. So first, and also Minecraft is a very open-ended, complex environment that really tests the capabilities of AI in general and LLMs specifically to the limit. So what they did is that they combine all the different components into an open world agent. First one is that one agent is teaching another agent how to do things in Minecraft. So there is a GPT-4 agent that is creating tasks for a GPT 3.5 agent, and then increasingly increase the difficulty of the test. So the first are some very simple tests like mine wood or kill a zombie, and then it becomes more and more difficult. And as we'll see in a second, this is a very important aspect of how the agent is working. So agent communication, a very important part. The second one is self-reflection. The agent is not communicating with Minecraft through vision because it doesn't see anything, and it also doesn't control the keyboard. It communicates with the environment thoroughly using code. And this code can be very complicated. So what they did here is that they built a self-reflection mechanism that the agent is writing a code, getting back the results, and then fixes the code until it reaches resolution. So it gets a sort of, okay, maybe we had some syntax error, maybe the code is working, but it's not performing the actual task. So there is one agent that is writing the code and another agent which observes the first agent and then tells him how to fix the code. So self-reflection and also a chain of thought. And the agent is also having long-term memory, which is a very important aspect of the agent. It has what we call a ski library. So each piece of code is written in a way that it can be used later for other tasks. So this makes the agent much, much more complex. And they also, which is something that is more of practical consideration, but for any one of you who wishes to build agents is very important, they divide the tasks between GPT-4 and GPT 3.5. GPT-4 is used for very complex reasoning tasks, and GPT 3.5 is used for more NLP simple tasks. And then this agent achieves state-of-the-art results much, much better than other agents. This is in the blue line. This is blue line, and the orange line, this is our Bost Voyager. And this one is AutoGPT, which for my surprise was actually able to do something. And these are the React agent, which were basically didn't do anything. Even React with reflection, which is the red line, was not performing very well. And they saw that each one of these components that we just discussed is increasing the results. So the agent communication with curriculum learning, if we don't use it, we get almost 93% degradation of performance. Without reflection, we get very big degradation of performance. No long-term memory means that it's unable to do difficult tasks. And when GPT-4 is used for coding instead of GPT 3.5, it actually works much, much better and give a X5 boost of performance. Let's see the time. All right. Okay. Okay, in the final paper we'll discuss today, the authors venture slightly into the realm of science fiction. And I think that by this point, I think at least some of you know this paper. So in this very interesting work done by Stanford University and Google, they built a sort of a, seems like a simulation for a LLM agent. In order to achieve this, the authors first create 25 agents and give them some initial personality and initial tasks. And the first component of this agent is the memory. Each observation and each action that the agent is doing is stored in the memory. And the memories themselves are ranked not only by semantic similarity, but also by importance and recency. So whenever the agent is pulling something out of his memories, there are several considerations. And also once in some time, the agent is getting several memories together and creates a sort of reflection. Like if it says, okay, I have a memory that I did a research on the library, and then another memory that I did a research on the university, then there is a reflection that I love researching. Second one is the dialogue. The agents themselves can communicate between each other using natural language, and the dialogue itself is affected by previous interactions and relationships which are pulled from the memory stream. And finally, the agent is doing planning and task execution. So the agent is getting a sort of a big task, and then it divides the task to smaller and smaller subtasks, which eventually fill its day. And obviously, at any point, it can deviate from the plan like we humans do, according to results of previous tasks or some interaction that he had with other agents. And what was most amazing in this paper is that we had emergent social behavior. One of the examples is one of the agents was running for mayorship, and by the end of the simulation, half of the agents in the simulation knew that he was running and even had some opinion about it. Another agent had a secret crush on another agent, so she invented a Valentine's Day party and she invited all the other agents in the city, and actually some of them showed up on time to the party, and also the secret crush arrived as well, so a happy ending there. So to finish up, and the last subject is how we can use this concept of agent to change how we work. So, I think the first concept that we can think about is about knowledge sharing. We want eventually each piece of knowledge that we give other people to come to them in the right time and in the right context. So we can create agents for the employees themselves. It won't be a digital clone, but more of the essence of what they are working on right now, what kind of information that they need. And then the information itself become a sort of an agent that can travel through this cyber space of the company and get to the right people at the right time. So this knowledge sharing problem becomes an agent-to-agent communication problem, which makes it much, much more effective. The second one is a sort of a replacement to a project manager. Imagine that you have in work many complex multi-step tasks involving multiple stakeholders. Agent can manage this task. So you can take this kind of baby AGI, tell him this is the steps that we have, and now go ahead and make sure that every person in the chain is doing what he needs, and the agent can do it. It's not super complicated. So they can give clear instruction to everybody in the process. What are the next steps? Who are the people that need to know? And so on. So at Everminds, we use this and much more to tackle one of the most significant workplace challenges, which is syncing. There was a recent research that the average worker wastes nearly 60% of the work time on digital communication, which is mostly syncing related. And our vision is to empower organizations to sync seamlessly using AI agents. This would enable teams to collaborate if they were in the same room without actually need to be in the same room, without even actually needing to be on the same time zone. And if you're interested, we are launching pretty soon, so you are welcome to join our waitlist at Everminds AI. And thank you very much.